we introduce GAPartNet, cross-category domain-generalizable object perception and manipulation via generalizable and actionable part. We construct a large-scale part-centric interactive dataset, GAPartNet, with rich, part-level annotation for both computer vision and interaction tasks. It has 9 common part classes, and provides semantic labels and pose annotations for more than 8,000 functional part instances on over 1,000 objects from 27 object categories. In GAPartNet, parts from the same part class share similar geometry, which allows generalizable visual recognition. They also have aligned actionability and can be manipulated in a similar way, which ensures minimal human effort when designing interaction guidance to achieve generalizable and robust manipulation policies. We then investigate 3 cross-category tasks: part segmentation, part pose estimation, and part-based object manipulation. Our method is trained on seen object categories, and needs to generalize to unseen objects categories. Parts are fundamental building blocks of our daily objects. We human can identify a set of commonly used parts, such as buttons and handles. Even on novel objects, we have no problem with recognizing the parts and we know how to interact with them. We thus argue that some part classes are more elementary and fundamental than object categories and thus worthy of more research efforts. However, existing interactive datasets such as PartNet Mobility and AKB48 datasets are all organized by object categories, thus they don't support the study of part perception and interaction problems across different object categories. To this end, we construct a large-scale part-centric interactive dataset, GAPartNet, with rich, part-level annotation for both computer vision and interaction tasks. It has 9 common part classes, and provides semantic labels and pose annotations for more than 8,000 functional part instances on over 1,000 objects from 27 object categories. In GAPartNet, parts from the same part class share similar geometry, which allows generalizable visual recognition. They also have aligned actionability and can be manipulated in a similar way, which ensures minimal human effort when designing interaction guidance to achieve generalizable and robust manipulation policies. We develop a systematic pipeline to process and annotate GAPartNet. First, we collect objects from existing datasets, PartNet Mobility and AKB48. However, some objects from existing datasets have missing surface areas due to 3D scanning, or have other modeling errors. If we identify such quality issues, we use 3D editors as well as other methods to remesh and fix these issues. Second, we identify all part instances in the object, and fix the kinematic chains to ensure that all parts are well segmented into separate links. For example, in some cases, handles are considered as a same part with the door. We manually separate and merge all the meshes and fix the kinematic chains, to ensure that parts are well segmented. Thirdly, we find that the original data didn't come with consistent part labels, so we annotate all the part semantic labels for AKB48 objects, and fix many labels for PartNet Mobility objects according to our definitions, to ensure our part labels are consistent across object categories. Finally, we use extensive rules, along with an annotation interface to align the functional parts with their canonicalized poses, and annotate the part poses. Given the part and pose definition, we then investigate 3 cross-category tasks: part segmentation, part pose estimation, and part-based object manipulation. Our method is trained on seen object categories, and needs to generalize to unseen objects categories. Our tasks are challenging due to the following reasons. First, the context of a part class can vary significantly across different object categories. For example, in coffee machine category, round handles usually sit on the top of lids, whereas for table category, they often stand to the front face of the drawers. Second, parts from different part classes may be in different sizes. For example, a round handle is usually much smaller than a door. Third, object parts in the real world distribute unevenly and a particular part class may appear with different frequencies throughout various object categories. Accordingly, we introduce several important techniques to facilitate domain-invariant learning. Our method significantly outperforms previous methods and achieves 76.5% AP50 on seen object categories and 37.2% AP50 on unseen categories. We visualize the results for different methods on seen and unseen category where red blocks show the failure cases. Our method has significantly fewer failure cases. Here we show qualitative results of pose estimation. The first row is our prediction, while the second is ground truth. In this work, we also set up a benchmark on cross-category part-based object manipulation in Sapien simulation environment, including 4 tasks: opening drawers and doors, using handles, and pressing buttons. To examine the generalizability, we collect novel objects from seen and unseen object categories to construct test sets on seen and unseen categories. Given the predicted part poses from our networks, we devise simple heuristics to generate grasping poses and complete the tasks, thanks to our interaction-aware part pose definition. Here we visualize the interactions and show that our method enables more human-like interactions, while RL algorithm from many skill benchmark often tries to open a door or a drawer by prying and rubbing the edge of the door or drawer instead of utilizing the handle. We further examine our method in real-world experiment and show that our method is robust to domain gap and thus can generate reliable part segmentation and poses prediction, and finally succeed in manipulating parts from novel objects.